Hello everyone. In this video we're going to look at how we use sensitivity analysis on the state of nature probabilities in order to figure out for what range of probabilities will a specific decision be the optimal choice to make. So anytime we talk about sensitivity analysis, what we are doing is seeing how much we can tweak some variable in the system and how much the tweak of that variable will adjust the outcome of the model that we're looking at. So here, because we're looking at doing this with the state of nature probabilities, what we will be looking at is how much we can alter S1 and S2. And we will only be doing this, when we have two states of nature. So I'm going to do this on a question that is very much like something you will see in one of your assignments. We're given a payoff table here, and here we're told that the payoff is profit in millions. We have three separate decision alternatives and two states of nature. So what we want to see is for what range in these states of nature, and specifically the probability of state of nature 1, as we alter the probability of state of nature 1, at what point will the different decisions be the optimal decision? When will I choose D1? For what state of nature will D2 be the best choice? And that's what we're trying to decide here. As I said, this is set up very much like one of your assignment questions. So let's begin and see how altering the probability of state of nature 1 will have an impact on our various decision alternatives. One of the first things we're going to need to do when we have a question like this is we're going to need to create the equation of a line for each of our different decision alternatives. Here, where we have three decision alternatives, we're going to need to create the equation of three separate lines. So let's begin by choosing some arbitrary value for our probability of state of nature 1. And again, I said I'm choosing state of nature 1 because back in the question, I was asked everything about probabilities for state of nature 1. I could easily do this for state of nature 2 as well, and I would get the same decision. The only issue is if we did it for state of nature 2, we'd have a little bit of extra work to do when we're finished all our equations. So as we said, as we're dealing with state of nature 1, let us assign the variable of P for probability to be associated with whatever probability state of nature 1 is going to have. Now, the reason why we can do this with two states of nature is simply because we always know what state of nature 2 is going to be if we have state of nature 1. Those two things, if there's only two possible outcomes that can happen, those two outcomes need to add up to 100% or a probability of 1. Right? So if state of nature 1 was 10%, then state of nature 2 would have to be 90%. Similarly, if state of nature 1 was P, then state of nature 2 would have to be 1 minus P. The two of these variables have to add up to 1, or 100% of the potential outcomes of this experiment. So now we're going to calculate the expected value of each of our decisions, but not with a given exact value for the state of nature probability, but with a variable for those probabilities. What I mean by that is normally where I would calculate the expected value of D1, if I was given that state of nature 1 was a 20% chance, and therefore state of nature 2 an 80% chance, I would do my payoff of 8, or 8 million times 20%, plus 7, or 7 million, times 80%. I would add those together, and that would be my expected value for decision 1. I'm doing the exact same thing here. Is just instead of subbing in an actual value, I'm subbing in the algebraic equivalent to that. For S1, I'm subbing in P, and for S2, 1 minus P. And now I will just simplify this expression, multiplying through the brackets, combining like terms, and eventually ending up with an expression. P plus 7 is the expected value of D1. And now I'm going to go and do the same thing with D2. So subbing in P where I normally would my state of nature probability, I end up with P times 14 and 1 minus P times 5. Again, simplifying that, Combining like terms, we end up with the expression 9p plus 5. Doing that one last time for D3. Again, we have to do this for every single decision alternative that we have. So expanding that out and combining like terms. Now what we have here, these are really equations of a line that we can now graph two-dimensionally. The reason why I know that they're equations of a line, a linear equation is any equation that has variables with no exponents higher than 1. So here, each of these expressions has a variable with an exponent of 1, an unwritten 1 on each of these p-values. And because there are no squared exponents or cubed exponents, as soon as we start dealing with squares and cubes and anything higher than 1, then we're starting to deal with equations of curves and parabolas and stuff that would be beyond the scope of our ability at this point. But these are very simple linear expressions that we can graph, which we're going to do next. So remember these 5 expressions: p plus 7, the expected value of D1, 9p plus 5, the expected value of D2, and 29p minus 9 as the expected value of D3. Those are the things that we're going to graph, and that's what we're going to do on the next slide here. So starting with the expected value of D1, which we just found to be p plus 7. Well, if this truly is the equation of a line, we simply need 2 points that we can plot. And then that straight line will easily go through those 2 points. You can choose any points you want in order to create that line, but I'm going to give you a suggestion of what I like to use. So the way we do this, on our graph, the p-value will be represented along the x-axis. The expected value will be represented along the y-axis. Now our x-axis can only go from a minimum value of 0. You cannot have a probability less than 0. And it can go to a maximum value of 1. 1 or 100%. Something cannot happen more than 100% of the time. And those are the 2 values that I'm going to use to sub in for p. I'm going to sub a value for p into this equation and see what value I get as I solve for it. So like I said, the 2 values I'm going to use are 0 and 1. Well, if I sub in 0 into this expression here, replacing p with 0, I get 0 plus 7, or that is equal to 7. Now I have a point that I can plot on this graph. As we said, the p-value is our x-coordinate. X along here. Well, 0 is way down here. 0 is right on the y-axis. And then our y-coordinate, the expected value of 7 or 7 million. So right about here somewhere, we will have a point that we can put on this graph. Similarly, I'm going to sub in 1 now, the highest possible probability that I could have. Subbing in 1 plus 7 is 8. And again, now I have another point I can graph here. So here I've got a value of 1 along my x-axis and a point of 8 somewhere up around here. I will put another point on the graph. What I can do now is connect those 2 dots with a straight line. Again, that's a linear equation, a straight line. With this line now representing the expected value of decision alternative 1. We have a very slight increase. What this is telling me is that as the probability of state of nature 1, remember everything we're doing is altering state of nature 1. This x-axis represents the probabilities associated with state of nature 1. So as this line goes up, the profit or the expected value of decision 1 is slightly increasing. That is the significance of this line. It represents exactly how much profit I expect to make from decision alternative 1. Now I'm going to create the same thing for the expected value of D2 and D3. So our expected value that we found on the last slide of D2, the equation we solved was 9p plus 5. And similarly, I'm just going to plug in 2 x-coordinates, or the probability of 0 and the probability of 1 into that expression. So as I sub in 0, 9 times 0 is 0 plus 5. We get the value of 5. So once again, we have a point that we can plot on our graph. where x is 0 and y is 5. Subbing in 1, we get 9 times 1 plus 5 is 14. So as I sub that in, we have our second point. And now connecting those two lines, now I have a new line which is representing the expected value payoff of decision alternative 2. And finally, I'll do that one last time with decision alternative 3. Subbing in 0, getting minus 9. And then subbing in 1 into that expression, getting 29 times 1, giving 29 minus 9, or 20. And now with all three lines plotted on this graph, and remembering that these three lines represent the expected value payoff of each of these decision alternatives. So here where we're talking about profit, if I'm talking about profit, I always want the highest profit. As I go along from a probability of 0 up to a probability of 1, what I want is the most profit possible. So I can see here, down here for low values, the blue line is the highest. Then all of a sudden the red line is the highest. Then all of a sudden the orange line is the highest. These represent different points at which my optimal decision will change. At each of those intersections, always wanting to choose the highest possible expected value. What I'm going to do is highlight those intersection points that deal with only the highest lines. So at this point here, I have a transition between one decision and another. Again, because I always want the highest line. At this point here, I have another transition point where the highest line changes. So everything below this low line, everything below here, the blue line or decision 1 is always the best choice. Everything up to this point, from a probability of 0, I have the blue line being the highest, the highest, the highest. As soon as I hit this point, all of a sudden that switches to the red line. Similarly, at this transition point, everything above this point, the yellow line or D3 is the optimal decision. It will generate the most profit. And then in between those two, that is where D2 is generating the most profit or has the highest expected value. And notice that this intersection point never factored into what I'm talking about here, because at this intersection point, neither the blue line nor the yellow line were at the highest point of which I would have chosen them. I only deal with the intersection points that deal with the optimal decision transition. So starting from 0, going along the blue with it being the best, then switching to D2, having it be the best, and then for higher probabilities of S1, having D3 be the best decision. Well, so I know definitely for low probabilities, D1 is the optimal decision, and for high probabilities, D3 is the optimal decision. But what I can do is to mathematically figure out at exactly what point that transition takes place. But as we do this, pay attention to the graph. Let the graph give you an idea. As I look at this graph, I can see that this first transition happened somewhere between a probability of 0.2 and 0.3. I can see that this second transition happened somewhere right around a probability of 0.7. And as I do the math should bear that out as well. So to figure out exactly what the value of this intersection point is, well, that is the point where my expected value of decision 1 and my expected value of decision 2 intersect. So if I set those two expressions equal to each other, what I will be able to do is to solve for the exact probability that that transition takes place. Well, the expression for my D1 line was P plus 7, and the expression for the D2 line was 9P plus 5. We found that a few slides ago. And now I have an equation where I can go and I can solve for P. Again, dealing with stuff that we should be able to do by this point, solving this algebraic expression, combining everything with a variable on one side and everything that's simply a constant on the other, we end up with minus 8p is equal to minus 2. Dividing the minus 8 to the other side, getting p is equal to minus 2 divided by minus 8, or a value of 0.25. And as we said, the math bears out exactly what our eyes are telling us on this graph. We knew that this point should have been somewhere right between point 2 and point 3, and the math is telling us that it is somewhere right between point 2 and point 3, or specifically a probability of 0.25. I will do the exact same thing at my other inflection point, or my other transition point, the point at which D2 is now equal to D3. So subbing in those two expressions, again, D2 being 9p plus 5, and D3 being 29p minus 9, solving for that algebraic expression, we eventually end up with p is equal to minus 14 divided by minus 20, or a probability of 0.7. And again, the math has borne out exactly what our eyes were telling us, that that probability should have been somewhere right around 0.7, where in fact here it is exactly 0.7. So now we have our two transition points at which our decision changes. Everything below 0.25, we are going to choose D1. Everything above 0.7, we are going to choose D3. And then everything in between 0.25 and 0.7, we are going to choose D2, which is exactly what this question has asked us. And so now we just go and fill in the blanks. For values of state of nature less than 0.25, D1 is going to be the recommended decision. For values between 0.25 and 0.7, D2 will be the recommended decision. And finally, after that second transition point, after 0.7, everything above there, D3 becomes our recommended decision. And again, that is because we were always looking to choose the highest line on that graph because we are dealing with profit. Real quickly, I'm going to show you what that would look like if we were dealing with a cost example. So keeping everything else the same, if this was a cost example, well, now we want to choose the lowest possible line. So I can see for my low values, well, over here, the yellow line, or D3, is the best decision. And only at this point does our D1 expected value become the best decision. And never at all is this red line factored in. Never, if this was a cost example or a minimization problem, never, ever, ever would I choose this red line, or D2. I would only be deciding, am I better to choose D3 or D1? They are the only two that are going to give me the absolute minimum cost that I would pay. So again, what I would do is see where is any intersection point which will change my optimal decision. In this case, there would only be the one. Everything below that transition point, we would choose D3. Everything above that point, we would choose D1. And again, mathematically, we should be able to find out exactly what value this would be. But our eyes on the graph are telling us that it's somewhere between 0.5 and 0.6. And it looks like it's a little closer to 0.6 than it is to 0.5. So mathematically, that should work out as well. Well, what I would do here is simply set my D1 line equal to the D3 line, or p plus 7 is equal to 29p minus 9. Solving that algebraic equation, eventually ending up with p is equal to minus 16 divided by minus 28, or a probability to 3 decimal places of approximately 0.571, which again is backed up by exactly what we're observing with our eyes on the graph. Okay, thank you guys. I hope this video helps you. Please email me with any questions that you may have.